Okay, recall this program that we wrote for fitting a line through a bunch of noisy data. Okay, now we just saw what we mean by mean squared error. Um, Actually, if you type in LM, which is the output of this program, it actually gives you the root mean square error, 0.51. But let's actually compute it. Let's actually compute uh, the quantity. Okay, let's compute mean squared error from scratch. Okay, let's mean squared error. Okay, let's actually compute it. How do we compute it? We have to first find the square error. The square error is basically y list minus b naught plus b1 times x list. Okay, um, so for a given value of x, b naught plus b1x is the prediction for y, and then you subtract that prediction from the actual value of y in your data set. So, and if you want to do all the data all at once, then you just go y list minus this thing. MATLAB is happy to do these vector um, manipulations or vector operations. Okay, so we can go error list equals this. This is actually the error list. Okay, so if I run this thing, we can just run that section. We get this to be the error. Okay, this is the error list. If you want, we can actually plot figure. Well, let's actually plot it on the same plot, figure 1, basically. It looks like that. It looks like that just because for the same reasons we have to do a scatter plot, which we can do by putting that. We can close this, run the whole thing again. Okay, so this is the error, right? So this error that we plotted as a function of x is actually the blue data point minus the corresponding value on the red line. That's this thing. Okay, it's basically the distance between this red line and the blue dots in the vertical direction, right? It's not perpendicular to the red line, it's actually in the vertical direction. Okay, so that's this thing. If we used some other weird value of b naught and b1, so we've now used the actual optimal values of b naught and b1. Let me actually, oops, let me oops, I keep the wrong thing. Let me, I'm struggling to use my mouse for some reason. Copy, paste, copy, paste. Instead of b naught and b1 drawn from here, so recall that b naught is 2.9 something, b1 is 2 point something. Instead of something, let me just like make up some random numbers. Let's say b naught is 1, b1 is like 5 or something. It's just some other thing. And let me run the whole thing again. Okay, so if you notice, this yellow dots are the error if you use the correct values of b naught and b1 that correspond to this line. If you just make up some random values for b naught and b1, you get error, which is this now. This is the error. Horrible error, right? So for these values of x, the error is much, much higher. Okay, so we can even like just change b naught and b1 slightly. So let's say it's b naught plus 0.1, and then here we go b1 plus 0.1 or something. and run this thing. Um, and you will notice that this magenta dots are a bit more than the yellow, a bit higher in value than the yellow dots. The yellow dots is the minimum error possible in terms of this mean squared error, and then the magenta dots are not quite optimal, right? So in any case, that's sort of something I wanted to show. Before, let me just run the whole thing again so that we clean this up. Okay, so that's the error. We can put a legend there. This is the minimum error. It's not just any old error, it's the minimum error possible in terms of mean squared error. Okay, so let me just run that thing. That's the minimum possible error that we can get in terms of this quantity. Okay, let's actually compute the mean squared error. So this is the error list. You get a list like this. If you want to go MSE, which is the mean squared error, okay, you first take the error list and then need to square it. You want to square every single element of it. If you want to do what's called element-wise operation in MATLAB, you go dot to the power 2. So this now takes the square of every single element in error, and then you go mean of that. That's going to be the mean squared error. Okay, that's the mean squared error. And then if you want the root mean squared error, RMSE, that's basically square root of MSE, and we can run this thing. And notice that we get 0.507, which is 0.51. And then if you type in LM, the linear model that we got from FitLM, it did say the root mean square error is 0.51. Okay, so that agrees. So we've computed the mean square error and the root mean square error correctly. Okay, so I was demonstrating how for a given value of B0 and B1, if you use the B0 and B1 that you get from FitLM, the mean square error is going to be small. If it's anything else, it's going to be larger. So what we can do if we want is fix B1 basically at B1, and then we can plot the mean square error as a function of B0. Okay, so what is our B0? B0 is 2.96. So let's actually do linspace 0 to 6, maybe 100 points in between, and then go for I equals 1 to length B0 list. We can say B0 not optimal, let's say, because it's not an optimal thing, equals B0 list of I. Now, I actually avoid using I these days. I say something like I loop or something, because in MATLAB, the variable I also means the imaginary number I. Okay, in any case, we can do this, and then we can compute the mean square error for that value of let me just paste this thing. Oops, certainly not just that thing. What I wanted to paste was this whole thing. Copy, paste. So we compute using this B0 not optimal, that thing, error list. Let me delete these things. And then mean square error list is basically this error list of this. And then I'm going to store all the mean square errors like so. So for each value of B0 not equal to the optimal B0, I'm going to compute the mean square error, and that's basically what I've done here. And then I'm going to plot, say in figure 2, B naught list, comma, MSE list, and X label is value of B naught, and Y label is mean square error. So what should we expect? We should expect a curve, a U-shaped curve, where the mean square error is high or higher than the optimal mean square error that we computed here if B naught is different from the value of B naught that we computed here. So let me run the whole thing. Okay, so we get this. This is the mean square error as a function of B naught. And if you look at it, it's a U-shaped curve. And then you can zoom in to where it has the minimum. And you will notice that it's very close to 2.96, which is the optimal value of B naught. Okay? So that's what we mean when we say this B naught and B1 are the best possible B naughts and B1 in the sense of mean square error. Among all possible B naughts and B1s, for each possible B naught B1, we can compute the mean square error. And then if we find the B naught and B1 that minimizes that mean square error, we get these ones. Okay. Something you can do is actually make this plot two-dimensional. You can do a surface plot in terms of B naught on the x-axis, B1 on the y-axis, and the mean square error on the z-axis. And then again, you will see a y-shaped plot, U-shaped plot or bowl-shaped plot for the mean squared error. And the bottom of that bowl will be at B naught equals this value and B1 equals this value. Okay, let me stop there, and then the next two little lectures are going to be computing these B naughts and B1s using simple formulas or general formulas. Okay.